Hello, everybody, and welcome to the week 14 video for Math 4400. This is the last video for the class. Just a few quick reminders. Your homework is due Monday at midnight. You have a quiz on this video due Tuesday morning, 8:30. Your exam 3 is on Thursday next week, and there'll be a review session in class on Tuesday. So just as always, we'll do that review session on Zoom, and it'll be recorded and posted afterwards. But come ready with any questions. If you have a chance, go over the exam materials that are posted, so you're ready with any questions before Tuesday. So what were the key takeaways from the last 2 weeks? It's been, because we had that snow day, it's been 2 weeks since we've had a video. And so, well, in that time, we sort of studied quadratic congruences. In particular, what we really developed was how to use the rules for the Legendre and Jacobi symbols to find if a number A is a square mod P or a quadratic residue mod P. And that's really the big takeaway. Like what I want you to be able to do and like what you'll have to do on the exam. And you should know some other things, you should know some concepts, but like the main computational thing is like using these rules in order to like compute a Legendre symbol in order to decide if A is a square mod P. So this week we sort of did, we added a little bit to that. So we talked about Euler's criterion and Eisenstein's criterion. These give you two like more or less explicit formulas for the Legendre symbol. And these played a big role in sort of actually proving these properties of the Legendre symbols that are so useful for computing. And somehow like the main thing here, the main takeaways to bring forward and to like have ready for the exam are sort of, you should know what Euler's criterion says, you should know what Eisenstein's criterion says, you should be able to apply them like in some simple examples. You don't need to worry about sort of like having memorized the proof of quadratic reciprocity using Eisenstein's criterion or anything like this, but you should sort of have basic familiarity with like how to use these to actually compute. Okay, good. So that's what we did. Yeah, and so in class, we've really given a complete proof of the properties of the Legendre symbol. There's one small note we should make. I mean, the Legendre symbol is where sort of the thing in the bottom is a P, is a prime number, P. We talked about this sort of more general thing called the Jacobi symbol, where your thing in the bottom is allowed to be any odd integer n. So like maybe a product of odd primes. Then the Jacobi symbol for A over n, where A is something that's in the units mod n or has GC 1 with n, is just defined to be the product of sort of the relevant Legendre symbols. So we define the Jacobi symbol of A over n to be the product. The Legendre symbol is according to the factorization of n. And what I told you in class and what we used when we were like making computations, like for example, in order to apply reciprocity, quadratic reciprocity, without having to factor first. So what we used there was that the Jacobi symbol satisfied all the same properties as the Legendre symbol. And so you might ask, like, do you need a separate proof for this? And the answer is basically no. It's actually really easy to check that once you have those properties, so those 4 properties, multiplicativity, the -1 law, the 2 law, and quadratic reciprocity, once you have those for the Legendre symbol, they actually sort of port over as is for the Jacobi symbol. And that just follows from just the corresponding rules for the Legendre symbol and this definition. So it's like fun to work it out and sort of check, but like, for example, you can sort of just check that the 2 law holds, for example. Okay, so do that if you're interested in, but I mean, somehow the key thing was to establish these for the Legendre symbol, and then they hold for the Jacobi symbol is not too difficult, just from this definition. Okay, so I want to talk a little bit more about quadratic reciprocity in the rest of this video. And I don't want to say much, I just want to sort of give you a sort of a different perspective on things. I think is sort of interesting and fun. And one thing we talked about is like quadratic reciprocity and the Legendre symbol, like it lets you tell whether something is a square mod P. It doesn't give you a formula for the square root. What's sort of interesting is that we can actually, like, there are other proofs of quadratic reciprocity. I mean, there are over 200 proofs, I think I mentioned in class, so I mean, somehow like there are lots of different proofs of this. And some of them you can sort of adapt to actually give you formulas for the square roots. Now, some of these formulas, they're not so good in the sense that like they're not really any better than doing guess and check because of sort of the things they require doing. But in some way, like you really at least you can find a formula in some sense. And but there was one particular proof where and one sort of particular kind of formula where it sort of really shows you something quite beautiful. Some relation between the complex numbers and sort of finite fields, like the field of p elements. So I just want to say a couple words about that. So here's a motivating example. So if I look at the complex numbers, I'm going to write this number as zeta sub 8. That's going to be 1 plus I over square root of 2. So here it is, so it lies on the unit circle. And like the key property of this number is sort of zeta. So if I take this number, zeta sub 8, and I raise it to the 8th power, this is equal to 1. And if I take it to the nth power for n less than 8, I don't get 1. So somehow 8 is the first power of this number that gives you 1. The reason sort of the 8th power of this number gives you 1 is like, well, when I sort of take a complex number on the unit circle and I sort of multiply with itself, like I just sort of double the angle. So here, more generally, if I sort of take two complex numbers and I multiply them together, I just add the angles off the x-axis, and then I sort of multiply the magnitudes. But if they're both on the unit circle, like there's no multiplication in the magnitudes. So like here, like this sort of starts at 45 degrees, square is 90 degrees, cube is, so I better use radians. So pi over 4 radians, pi over 2 radians, 3 pi over 4 radians, pi radians, 5 pi over 4 radians, 6 pi over 4 radians, 7 pi over 4 radians, 2 radians. So back here, after I do it 8 times, I've rotated back to an angle of 2 pi, and I sort of landed where I landed at 1. That's sort of the first multiple that gives you 1. It gets you back to 1. Or first power that gets you back to 1. Good. So that's sort of the key properties. So such a number is called a primitive eighth root of unity. In general, like a primitive nth root of unity is some number whose nth power is 1, and there's sort of no lower power that's 1. Good. So they're pretty easy to write down in the complex numbers, like this one. Like in general, you sort of just look at it. You want primitive nth root of unity, so look at the number on the unit circle as sort of an angle 2 pi over n. That would give you a primitive nth root. You could also write that as e to the 2 pi I over n theta, or e to the 2 pi I over n. Okay, anyway, that's what this is an eighth root of unity, a primitive eighth root of unity. But here's a cool formula. Turns out I can write down a square root of 8 using this primitive root and its powers and the Legendre symbol. So I take the Legendre symbol of 1 over 8. Okay, so and I should be careful, and that's not really defined because we didn't sort of let ourselves have even integers in the bottom. But I mean, the Legendre symbol of 1 over 8 here, I at least mean like is 1 a square mod 8 or not? Good. So I do the Legendre symbol of 1 over 8 times zeta 8 plus the Legendre symbol of 3 over 8 times zeta 8 cubed plus the Legendre symbol of 5 over 8 times zeta 8 to the 5th plus the Legendre symbol of 7 or 8 over 8 times zeta 8 to the 7th. Good. And so, well, 1 is a square, minus 1 is not a square, minus 1, sorry, 1 is a square, 3 is not a square, 5 is not a square, and 7 is a square. So that's just zeta 8 minus zeta 8 cubed minus zeta 8 fifth plus zeta 8 to the 7th. And well, like if you look at that, like you sort of get, when you add those all together, you're adding up these 2 points. So zeta 8 and zeta 8 to the 7th. And that's sort of killing their imaginary parts and just getting you that square root of 2. So you get 2 over square root of 2, which is just square root of 2 for the imaginary parts, for the real part. And then you sort of do the same thing over here. You add these up and you kill the imaginary part. You just get minus 2 square root of 2, or so minus square root of 2. And then you subtract that off because you have the minus sign here. And you get 2 square root of 2. Okay, and so when you do that, well, 2 square root of 2, if I square that, that is 8. So 2 square root of 2 is just another way to write the square root of 8. Okay, so when write this out if you don't believe me, and you can write down the coordinates of these write these 4 points as complex numbers and add them again, and you really get 2 square root of 2, which is just square root of 8. So here's the crazy part about this formula. Is this actually works not just over complex numbers, but in any field with a primitive eighth root of a unity. So again, so like what I mean by primitive eighth root of unity is just a primitive eighth root of unity is something whose eighth power is 1, but sort of no earlier power is 1. So 2, for example, you can check as a primitive eighth root of unity mod 17. If I do 2 to the 8, I get 256, and that's 1 mod 17, and it's the first time that happens. So you can just check that on your own Reason Sage. But I'm telling you 2 is a primitive eighth root of unity mod 17. Note that's differently. So when we say primitive root mod 17, that would mean like a primitive 16th root of unity mod 17. So here this is actually a square of a root, but anyway. So 2 is a primitive eighth root of unity mod 17, just like so in the field of 17 elements, just like this number, like 1 plus I over square root of 2 is a primitive eighth root of unity in the complex numbers. Now, the crazy thing is, like, if I do the same formula, so I do 2 minus 2 cubed minus 2 to the 5th plus 2 to the 7th. So here, just everywhere I had zeta 8, I wrote 2. Then I get 2 minus 8 minus 32 plus 128. You simplify that, you get 90, which is 5 mod 17. And lo and behold, 5 squared is 25, which is congruent to 8 mod 17. So the formula gives a square root of 5 in the field with 17 elements. I mean, this is completely bananas. I mean, somehow there's no reason, sort of some arithmetic with this like complex number. There's no obvious reason that if I sort of just take some complex number and do some arithmetic with it, sort of using powers and adding in differences, that should sort of match up with doing the same arithmetic with sort of the number 2 mod 17. I mean, so somehow this is sort of something very special about formulas with roots of unity. Okay. And how is this related to quadratic reciprocity? Well, you can actually use this to deduce the 2 law. So this formula lets you deduce a law for when 2 is the square root modulo p. Basically, the reason is because it produces a square root of 8, but somehow if I have a square root of 8, I get a square root of 2 by sort of just dividing by 2. So for example, and this tells you like in any, if in FP you have a primitive eighth root of unity, like it gives you a way to produce a square root of 2. But it's sort of with a little bit more work, you can actually sort of turn it into a way to sort of check for any like fixed p, like whether or not there's a square root of 2 in it. That sort of involves some more complicated math that we're not going to get into right now. What's cool with this is like you actually sort of, there are lots of similar formulas, and like there are enough formulas like this that you can actually use them to prove quadratic reciprocity. So these similar formulas are actually a little bit more difficult to establish, but they're not so bad. And so for example, like here's a formula for the square root of 5. Like if you have a primitive 5th root of unity, so here zeta 5 is a primitive 5th root of unity. Then you can get square root of 5 by taking the Legendre symbol of 1 over 5 times zeta 5 plus the Legendre symbol of 2 over 5 times zeta 5 squared plus the Legendre symbol of 3 over 5 times zeta 5 cubed plus the Legendre symbol of 4 over 5 times zeta 5 to the 4th, which is just zeta 5 minus zeta 5 squared minus zeta 5 cubed plus zeta 5 to the 4th. So you look at this sum of sort of these powers of this root of unity, the 5th root of unity, primitive 5th root of unity, and what you get will always be a square root of 5. And again, like this holds like whether this is a primitive 5th root of unity in the complex numbers, or whether this is a primitive 5th root of unity in a finite field, or so on. So this sort of always gives you a formula for square root of 5 once you have a primitive 5th root of unity. Right, so if you want to sort of prove quadratic reciprocity this way and sort of like use this to write down square roots, like there's this little hitch, and this is sort of like the reason I can't sort of explain this more is to use this, like to prove quadratic reciprocity, or even for the two law, like you need to be able to go up to bigger finite fields than the ones we've talked about so far. It's like, for example, we talked about like the field with 19 elements, F19. But there's not actually a primitive fifth root in F19. So if you want to sort of use this formula, you have to first go up to a larger place. You have to sort of do this field, like it's sort of like constructing the complex numbers from the real numbers by adding a square root of -1. You can sort of construct a new field by adding a square root of -1 to F19. We'll call it like F19 brackets I. And now this is still a finite field, but now it has 361 elements, which is sort of 19 squared. It is not the same as Z as like working mod 19 squared. Like sort of arithmetic here is not arithmetic mod 19 squared. It's really something new we haven't seen. And then if you go up to this field, you sort of can write down this formula for a square root of 5, and then you can ask, like, can I tell whether or not this number I get like lives in this inside of F19, or whether it's sort of only in this bigger field. But that's really something like we need to develop a lot more tools to go through this kind of proof of quadratic reciprocity. But it is sort of beautiful that you have these formulas that work in terms of roots unity for square roots, like somehow no matter what field you're working in. Okay. And so somehow, like, I mean, the advantage of the proof of quadratic reciprocity and sort of the things we discussed in this class were like via Eisenstein's criterion, it had this beautiful picture to it, counting dots. Like it gave us sort of some geometric insight into the problem, but I mean, every different proof sort of gives you some other insights. And if you sort of chase the ideas down involved in this proof, and this really leads to a lot of very interesting and deep mathematics. So, and so the tools you'd need if you wanted to understand that proof fully would be things called field theory and Galois theory. Those are things you would learn in Math 5320, which is Intro to Modern Algebra 2. If you'd like to take that, you'll learn lots of exciting things. And then, I mean, somehow that would let you prove quadratic reciprocity. But if you really want to understand what was going on there, if you really want to understand like how to generalize it and sort of like maybe it's like higher, like larger powers, and to really sort of get a like concrete understanding of all of the mathematics that's going into it, like all of the structure that's there, you need a subject called algebraic number theory, and an even deeper subject called class field theory. And these are the kinds of things you would learn in Math 6370, which is like a graduate number theory class, and sort of even sort of beyond that sort of in grad school. So if you like number theory and you want to learn these kinds of things, be careful, you might turn into a mathematician. But somehow, even if you sort of don't want to turn into a mathematician, you can still learn sort of a lot more about this if you take this Introduction to Modern Algebra sequence. And of course, there are many other pieces of mathematics to learn. I just wanted to sort of give you sort of one window into one possible way you could go. Okay, I will see you in class next week.